Now, we recall again the definition of Cp and Cf, right? Cv is the derivation of du over dt at constant volume, which means the pressure can change. Whereas Cp is the specific heat at constant pressure. Okay? And the ratio between those two is this, K. K is Cp over Cv, and this K is also still related with the R from Cp and Cv. Okay, so next time I give you a question, I give you Cp and Cv, don't ask me where is the R. You can calculate it. Or if I give you Cp and Cv, don't ask me the K, because the K can be calculated. Okay, remember that. So they are related, they are still family. Right? Now, why we keep talking about the enthalpy and entropy? Because for this compressible flow, those two is very important, and we will calculate our parameters using those. Okay. Anyone still remember stagnation pressure? Yes. What is stagnation pressure? The pressure at zero velocity. Yeah. Okay. This is the pressure at the point where the flow becomes zero. Right? From the moving fluid, suddenly you stop it, then you get a stagnation point. The same goes for the stagnation enthalpy. Stagnation enthalpy is the enthalpy value when you make the flow, the moving flow, into a full stop. Into a full stop. Let's say you have a moving fluid, suddenly you stop it, right? So on top of the enthalpy bring by the thing, the moving air, you will have additional enthalpy because you put this moving fluid into a full stop. Okay, you make it into a full stop. Then what is the consequence? The consequence is, because you know that delta H is equal to Cp times T, right? You know that? So if you stop it, you stop the flow, right? The temperature will be increased. Before going to that, for the compressible flow, we will mostly use this one rather than H1. Okay, we will use the stagnation properties rather than the static properties. So, coming back to that, if you have a very high kinetic energy, your K energy is very big, and then let's say you run, and then you hit the wall, what do you feel? Hurt? Okay, a very simple experiment. You do this. Okay, this one is moving, right? Moving. Now you do that. What do you feel? Do it again and again. You will get. Okay. The thing that I want to tell you is that if you try to stop the movement of something, right, and put it into a full stop, basically you will increase the temperature on that surface. Okay, if you don't trust me, you can try to do that. Okay, so you will get a higher temperature. Okay, and similar to your dynamic pressure, which is a function of velocity, this thing here is called a dynamic temperature. So this one is temperature increase due to the changes in the velocity. Right? Remember in your Bernoulli equation you have static pressure, dynamic pressure, and hydrostatic pressure. Here you have static temperature, and those things is called a dynamic temperature. Okay? And dynamic temperature is given by those V square over 2. How do you get it? Because you know that okay, H naught is equal to H at that particular point plus K epsilon, because we are not dealing with the changes in elevation, right? The elevation is still the same. So this one you put here velocity is equal to 0. This one you got velocity. So the enthalpy here is that H plus the TE. And this is Cp times T0. This T naught is the so-called stagnation temperature. Okay, so this one equal to Cpt plus K epsilon is V squared. Right? If you put m dot here, then it will become energy. If you don't put, it will become specific. You ask Dr. Zainal. Or who is your thermodynamics? 1. This one is in 1, right? Or in 2? You got all A, right? Anyone not getting A? Then you need to work harder. Okay, so this one is your stagnation temperature. So you got it T naught, or your stagnation temperature become T plus V square over Cp, 2Cp. Okay, because this one is V square over 2. Right. Now, once you get your stagnation temperature, using the thermodynamics practice, you can calculate the stagnation pressure and stagnation density. But remember, this thing only applicable when your flow is isentropic. Right? If you have ideal gas and isentropic condition, you get those. This. Okay, this equation is only valid when you have isentropic condition, ideal gas. If it is real gas, not working. If it is non-isentropic, it will not work. Okay, so it's only if you have isentropic ideal gas condition. Okay, so you get stagnation pressure and you can calculate the stagnation density. So once you know your stagnation temperature, you can calculate your stagnation pressure, and once you get your stagnation pressure, you can calculate your stagnation density.